Alright, in this video we're going to talk about Unit 2, Objective 4, chain rule. Chain rule is how we're going to deal with composite functions. So if we have some function we'll call h of x, and that's equal to some function f of g of x, our chain rule is going to tell us that the derivative of h is equal to f prime of g of x times g prime of x. So what we're going to be looking for when we see these composite functions are parentheses. That's where the big idea is going to come from. That's where we're going to see these, because not very often are we going to see a function labeled f of g of x. We're going to have to recognize that it is in fact a composite function. So there are three big ways that we're going to see composite functions in calculus. The first being just plain old parentheses with a power outside of it. So if we saw something like h of x is equal to the quantity 3x squared plus 7 to the 4th power. We see that, and the parentheses around the 3x squared plus 7 tell us that this is a composite function. If you want to break it down as a composite function, you could call f of x as something, we'll call it u to the, not second power, but 4th power, and we could call g of x 3x squared plus 7. So h of x would be f of g of x. Now, you're not ever going to have to do this, but you need to think about it that way. Anytime you see parentheses, that's going to set apart a new function. So if we're thinking about h prime of x for the derivative, remember that our chain rule said take f prime first. So take the derivative of the outside function first. So in our case here, the outside function is that quantity to the 4th power. So if all we saw was something to the 4th power, we know we would drop the 4 out front. The thing we took the derivative of, our inside function, is going to stay the same. Drop your exponent, and that's the derivative of the f prime part. That's f prime. Then we need to multiply it by the derivative of g prime. So the derivative of the inside function is 6x. So remember, our derivative says this: f prime of g of x times g prime of x. So we want to say the derivative of the outside part and then keep the inside the same. Notice how in our rule g of x stays the same. So when we took the derivative of our function here, the 3x squared plus 7 stayed the same, and then at the end we multiplied by the derivative of that function. So another place where we can see this is kind of similar. If we have something like h of x is equal to, I don't know, the 3rd root of, we'll just keep the same thing, 3x squared plus 7. It's kind of the same idea as what we just wanted to do, because we can't take a derivative of a radical. We have to get rid of the radicals by using powers. So when we rewrite this, we'd have something like that. So we'd have 3x squared plus 7 to the 1/3 power. And again, we have parentheses now in our problem, and those parentheses are going to tell us where the first function is. I'm sorry, that's not prime. The parentheses are going to tell us where that first function is going to be. So if we look, we see parentheses with the 1/3 power, so when we go to take our derivative, that 1/3 needs to drop down first. Keep the inside the same. Subtract your 1 from your power. Then we want to take the derivative of the inside. So on a problem like this, or a problem like the one before, you could stay here. Sometimes your multiple choice will stay here. But a lot of times AP is going to combine those things to simplify. So 6 divided by 3 is going to give us a 2x times the quantity 3x squared plus 7 to the negative 2/3 power is what AP is going to give for their answer. The third place where you're going to see chain rule is within trig, but trig is going to have its own video, so we're going to stop there as far as examples go. One thing I do want to say about chain rule is there's some people that call it the onion rule, and this might help you kind of think about what we're doing. They call it the onion rule because we want to peel away layers with derivatives. So if you think about an onion, it has a bunch of layers. You can peel the top layer out. You can then left with the next layer under that, and you could peel that layer away, and there's another layer left under that. You can think of the chain rule in the same way. So if we look at something like this, we get a bunch of different layers in our problem. So the outermost layer, anytime you see a new set of parentheses, that's going to give you a new layer to your onion, a layer to your derivative. Anytime you see new parentheses, that's when you want to think, okay, now I have a new derivative I need to take. So if we look at this problem, every time we see new parentheses, we have to think about taking another derivative. So on the very inside, there's no new parentheses. So we have three sets of things that we would need to do here. So if we took this derivative very, very quickly, remembering that we only want to take one derivative at a time, the blue derivative, we would drop the 2 out front. Everything inside, so the red layer and the green layer, are going to stay the same. I guess we could put a 1 there just to keep things consistent. So only thing I took the derivative of was the blue. The red and the green stayed the same. Now I want to take the derivative of the next layer in, so the red layer. Green layer stays the same. Then the next layer in is the green layer, so take the derivative of the green layer. And unsimplified, that is our derivative. Now obviously we can kind of combine some things. We have a 2, a 3, and a 6x, so that's going to give us 36x, and then we can just put, oops, I forgot my 7, sorry. We have a 3x squared plus 7 to the third, and a 3x squared plus 7 squared. So if you wanted to take it even farther, we could say 36x times 3x squared plus 7 to the 5th power. But the idea is we want to peel away one layer at a time, take one derivative away at a time, and that is our chain rule.